Good afternoon. My name is Markall, and I'm a software engineer at Continuum Analytics, where I work in the high-performance analytics group. So part of my job there involves working on the development of Numba, and the other part of my job involves using Numba for consulting to try and accelerate customers' codes. So what I'm going to try and do is share the benefit of some of that experience in this tutorial. So if you want to start getting set up right away, you can grab all the tutorial materials from this URL. There's the slides and exercises and examples online, and there's also tar.gz and zip versions if you want to download the whole lot to your computer. If you've not already got Anaconda or Miniconda installed, then you can install, then I'd recommend that you get Miniconda and then use it to install Numba by running conda install Numba. There's one or two of the examples that I've got, I think, have dependencies on SciPy and scikit-image as well, so you probably want to install those as well. Has everyone got this URL? Can I move on to the next slide? For the structure of the tutorial, what I'm going to try and do is do a very brief tour of the features of Numba to give you a sort of brief idea about it before doing a few exercises to get familiar with it. Then after a while, I'll come back and talk a bit more in depth about how it works. So, on with the tour. What is Numba? Numba is a tool that you can use to make your Python code go faster by compiling and specializing it just in time. It's an opt-in tool, which means that it only compiles the functions that you tell it you want to compile. The reason for that is that using Numba makes a trade-off. It has to relax some of the semantics of Python code in order to get better performance. You wouldn't want to necessarily make those trade-offs in your entire code base. You only want to make them for the bits of code that you care about accelerating. So that's why you only choose specific functions to use it with. Its development has been focused on making it efficient for numerical computation and array-oriented computing. So a lot of the trade-offs that have been made have been focused on doing that. Also, because it compiles stuff just in time, you can use it interactively, just as you would any other Python code. So these are some of the practical details of the implementation of Numba. It's a just-in-time compiler based on LLVM, which is the low-level virtual machine. The reason we decided to use that is because it's a fairly mature tool chain. It's got a lot of inbuilt optimizations. There's a lot of different other people using it in their compilation tool chains. And it's cross-platform. So using that allows us to focus on the specific aspects of compiling Python rather than doing lots of low-level sort of compiler work. Also, because we use LLVM, it means that we can target CPUs and CUDA GPUs. So for the purpose of this tutorial, I'm only going to focus on the CPU target because the GPU target is only applicable to a narrower range of codes. And it also doesn't hide the parallel thread execution semantics of the GPU. So it's a little bit more difficult to use. It runs on Python 2 and 3 on CPython. So we test with those versions, and you can use it side by side with any other Python code or any C extensions that you've got. So you can use it in the same code base as NumPy or SciPy or any of the other tools from the PyData ecosystem. It's BSD licensed and it's cross-platform, so it should be fairly easy to include within your own code bases. This is just a brief example of the kind of speed up that you can get using Numba. If we take a pure Python implementation running on CPython as a baseline implementation, we'll say that runs at a 1x speed. Then there's some things you can do to make it go faster. Just using NumPy, for example, you can vectorize it with array-wide operations, but you can do better using Numba. So if you use the CPU target for this problem, then it'll run 120 times faster than the baseline. So you can get an order of magnitude speed up over NumPy there. This is one of those problems that does work well on the GPU as well, so you can get a bigger speed up there. So to continue the Mandelbrot example, this is the code that was used with the Numba version. As you can see, it is just normal Python code. The only thing we've done to use it with Numba is to decorate it with this JIT decorator. Now, when the Mandel function gets called, instead of the Python source running, Numba will jump in and run its compiled version of the code. So this is generally how you would use Numba. You take your Python code and mark it with the JIT decorator. Now there are some things that some restrictions about what you can do in functions that you've decorated with this decorator, because as I said earlier, you have to make some trade-offs to be able to get the performance. So the things that you can do include all the normal control flow, so you can use things like if-else and all those other statements. You can raise exceptions from JITted code, and you can call other compiled functions as well. So if you have one function you've decorated with JIT, you can call it from another JITted function, and that call will be made through native code. There's no looping back into the Python interpreter. Also, those other compiled functions can come from C types or CFFI as well. And you can use generators inside JITted functions. There's some things you can't do as well. So although you can raise exceptions, you can't catch them. So there's no try, except, or finally syntax. As a consequence of that, there's no context managers, so you can't use the with statement. We haven't yet found an efficient way to implement comprehensions, so they're not supported in JITted code. And although generators are supported, yield from in Python 3 isn't supported. The other limitation to be aware of is that you can only decorate functions with JIT. You can't JIT entire classes yet, but that is going to change in the next couple of releases of Numba. So these are the Python types that are supported. You can use these primitives and anything that's like a buffer-like object you can use, so bytes or byte array as well. There's some built-in functions that are supported, which means that Numba provides native implementations of these functions that you can call from inside JITted code. It's not just the built-in functions that are supported. There's also support for other functions from the Python standard library and some third-party libraries as well. There is a comprehensive list of all the supported functions in the manual that you can have a look at if you need to check for a specific one. Hello. Yes. Lists aren't really supported, no. I mean, you can use a list, but it will fall back to a slower mode. I'll talk a little bit more about that a bit later. As I said earlier, a lot of the focus was on array-oriented computing, so there's been quite a lot of effort going into support for NumPy features. So you can use all types of NumPy arrays inside JITted functions, apart from when you're using arrays, structured arrays that contain Python objects. You can allocate arrays inside JITted functions, and you can do iteration and indexing and slicing. There's reductions, and you can use the scalar types and values as well. You can also write array expressions inside a JITted function, but you can't use broadcasting at the moment. Again, there's a list of everything that is supported inside the reference manual. So I've talked about one way of using Numba, which is to use the JIT decorator. The other way in which you can use it is to use it to write NumPy universal functions, or ufuncs, in Python. So if you're not familiar with what a ufunc is, essentially it's a scalar function that can be applied element-wise to array arguments by NumPy. So when you write one of these scalar functions, you also get some other operations for free that allow it to be used in reduction and accumulation operations. The downside of writing ufuncs normally is that you either have to write them in C and compile them, or if you write them in Python, they can be slow. But Numba provides a way in which you can write them in Python and have them compiled. So you do this using the vectorized decorator. If you write a Python function which takes scalar inputs and returns a scalar output, then when the function is called with array arguments, Numba will take care of compiling that scalar function to native code, and then NumPy will take care of applying it element by element. So ufuncs can be useful for element by element computations, but sometimes you might want to operate subarray by subarray or submatrix by submatrix. So this is where generalized ufuncs or gufuncs can come in. And you can also write these with Numba. They can operate on an arbitrary number of input elements. So to declare to declare a GU function, you can use the GU vectorized decorator, which is like using vectorize, but you would also need to tell Numba something about the inputs and outputs to the function. So there's two things it needs. The first thing it needs to know is the types. So in this example, the types of the two inputs and the output are int 64. The second thing you need to give it is a layout specification, which is this string. So in this example, we're taking an n-length vector and a scalar, and that maps to an output of an n-length vector. That's delimited by the inputs and outputs are delimited by the arrow notation. Now, functionally, there's no difference between the inputs and outputs. The only difference between them is that inputs are something that's passed in by the user, and outputs are something that gets allocated during the time, at the time that they're called, and then are returned to the user. So that means that inside your Python function, you can actually modify the inputs, and that allows you to modify things in place. These are a couple of other examples of layout specifications. So, for example, if you had a lot of matrix vector products that you wanted to compute, lots of matrices and lots of vectors, and you wanted to multiply them, then you would use this layout specification, taking you from an n by n input and an n-length input to an m-length output. This second example shows one of the limitations of the layout format, which is that all the sizes have to be symbolic, so you can't write a concrete value. So, for example, if you wanted to declare a GU func that would compute the maximum and the minimum of an input array, the output would be two things, but you can't declare it you can't declare the output as being of length 2. Instead, you have to use two scalars. Thank you. So that's pretty much it for sort of the brief tour of Numba. If you want to have a look at the first set of tutorial exercises, if you've managed to download them, if not, I've got the URL for accessing them up there. Then I'll try and help out if there's any problems, especially if there's any problems getting set up at the moment. And then I'll come back and talk a little bit more after you've had a go at the tutorial exercises in about 10 or 15 minutes. Are there any questions at the moment? Hiya.
Do you show different types? Don't have the type specified. Is there any performance benefit if I specify it?
So for the JIT decorator, it's optional to specify the types, and it's normally not worth doing because Numba figures out what the types are at the time of the function call. For the vectorized decorator, you might wish to specify a list of different types and the order in which they are, the order in which they can be, the order in which they're prioritized. And the reason for doing that is you may want to make sure that something with, for example, with a float 32 input doesn't get cast up to a float 64. Inside the second section of the first tutorial about the vectorized decorator, there is kind of an example about doing that as well. Hiya.
The CUDA support is a feature of the LLVM compiler? My question is, do you support OpenCL?
All right, no, there's no support for OpenCL, and there was a branch a while ago where we tried to do that, but it was very difficult to make it work very well because, so as I understand it, there's different memory spaces for different pointers, and it was difficult to get that to work efficiently because we kind of assume that the memory space is flat and all the pointers are in the same memory space in Numba. With the second bit of the presentation that I was going to go on with after you'd had some experience with the first tutorial exercise. So my plan now was to talk a bit about the internals of Numba and how it works, so you can get a bit of an understanding of what kind of things work well with it. So the things I'm going to talk about next are the dispatch process and the compilation pipeline. Then I'm going to talk a little bit about typing, so you can understand how things are typed in it, how to get around type inference problems. And then I'll talk a bit about the different modes of compilation. So what you were going to see in the tutorial exercises was that when you use the JIT decorator, there's a little bit of an overhead on JITted function calls. So that would mean that you would need to make sure that there was enough work done inside your JITted function so that the speed up of that function overcomes the overhead of the function call. So the reason for this overhead in calling JITted functions is because each time the function call happens, there's a dispatch process that Numba has to do. So Numba doesn't compile code every time you call it. Instead, it maintains a cache of compiled versions of functions of the function, where each of those compiled versions is specialized to the particular types of the arguments. So the first thing Numba's going to try and do is retrieve a compiled version from that cache. And to do that, it's got to look at what the types of the arguments in this function call are. Then it can compare those to the types that are in the cache. If it does find a match, then it can retrieve that version. But if not, it's got to kick off the compilation pipeline to build a new specialization. Once we've got a compiled version of the function, then we can't call that on the arguments we've got because they're Python objects. So they need to be marshaled into native values. For scalars, that's copying the value, and for arrays, it's getting the pointers to the data. Then it can call the native code function, and it will get a native return value that's got to be marshaled back into Python. So when compilation happens, this is the pipeline it goes through. First of all, it calls the Python compiler so that it will turn the Python source into Python bytecode. Then it does some analysis on that bytecode to build control and data flow graphs, and then a number intermediate representation. After that, it does type inference to generate a type for everything in the intermediate representation. And then it lowers that intermediate representation to LLVM's intermediate representation. And from there, LLVM generates the actual target machine code. Now, normally, you won't have any problems with these stages, these first 4 boxes at the top. Things tend to go smoothly there. Where you tend to get problems when you're trying to convert code to use Numba is during the type inference stage. If something's badly typed or something's gone wrong with typing, then you can get errors coming out of that stage. You can also get errors coming out of the lowering as well. That's normally because something's badly typed and it's managed to sneak past the type inference or the type checking stage. So next we'll look at type inference so that you can understand how to avoid problems there. But why do we actually need to do this? And the reason is that native code is statically typed, but Python code isn't. So Numba has to do something to determine the type of every argument, intermediate value, and return value in the function. It does that by propagating type information from the arguments through to the return values. It can do that because for every function that it supports, it's got a mapping from input types to output types, and it's got the data flow graph of the function, so it knows where to propagate those inputted and outputted types. So to understand it a bit better, we'll have a look at this example function. And we'll assume that it's called where A is a float 32 and B is a float 32. At the beginning of the type inference phase, it only knows the types of these 2 arguments. Then, when it propagates, it can deduce the type of C, because if you add a float 32 to a float 32, you get another float 32. Then it can deduce the return type, because that comes from the type of C, which is float 32. So that's a straightforward example. The typing's finished and the function can be compiled. Where it becomes a bit more complicated is when you've got control flow involved, because you can have multiple different types assigned to the same variable along different paths. And when those paths merge, you have to do something to unify the different types that came from the different paths. So we'll look at this example of the select function. Again, we'll assume that A and B are of type float 32. Now inside the if branch, the type of ret is deduced to be float 32. Inside the else branch, the type of ret is assumed to be float 32. Now, at the point of the return statement, the control flow merges. So we've got a type for ret from both branches. that means that we don't have a single type for it, but instead we've got a set of types. In this case, they're both float 32, so they can be unified into a single type. And then that's a successful typing, and the function can continue to be compiled. Now, if we look at another case where it goes wrong, was there a question? Okay. Now, if we look at another case where it goes wrong, this time, if we assume that A was a tuple, then inside the if branch, the type assigned to ret is a tuple, whereas in the if branch, the type assigned to ret is a tuple, and in the else branch, its type is float 32. This time, we build this set of return types for the return statement. And because it's a tuple and a float, we can't unify them, because there's no native value that is suitable for representing both these different types. So therefore, the typing's failed, and the function can't be compiled. In practice, what it looks like, if this has happened, when you get a unification error, is Numba will give you some kind of feedback like this. So this is one of the errors that I saw when I was working on the examples for this tutorial. It told me that this variable had unified to object. So unified object is any type. So that's telling me that unification's failed. Now what I'd done in this case was to treat this variable in one place as if it was an array, and in another place as if it was a scalar. So I'd done something functionally equivalent to this. And that was why it gave me that typing error. There's some other kinds of typing errors that you can get as well, which, when they occur, Numba tries to give you some kind of feedback about what the problem is. And the form of that feedback that it gives you is normally, it tells you that some kind of function for some particular types is undeclared. And the name of the function that it gives you is normally kind of similar to what the name of the function would be in Python anyway. So in this example, if you try to treat an array as if it's a scalar as if it's an array, then it might tell you that getItem is undeclared for a float 64 with an int64 argument. I often find that this kind of error happens when I'm getting a bit confused about whether something is, if I'm getting a bit confused about whether something is an array or whether it's a scalar, or if I'm getting confused about which dimensions of an array I'm working with. I did also say that you can get some errors coming out of lowering. And so I've got a couple of examples of those errors to show, just to help you with interpreting them, because they can be quite cryptic. So this is one, that I got working on the examples. Because broadcasting is not supported, the error message that you can sometimes get there is it will tell you that some particular internal value is not a valid parameter name. Now, I just happen to know from the experience of this error that it means that broadcasting is not supported. But my general strategy when trying to figure out where these errors are coming from is just to comment out different lines of the source code and to try running again and again until I can isolate the problem to a particular line. Then when it's narrowed down to a particular line, you can usually deduce what the actual issue is. This is something that can happen either in lowering or typing. Sometimes this happens when you're doing broadcasting, or also perhaps if you've got two different arrays that are sliced differently, or two arrays of different arity. Sometimes Numba will say, I don't know how to allocate an array with layout A. So if this happens, then look around at the broadcasting and slicing operations in your function, because they might be the source of the error. And the other kind of error that can sometimes happen if you treat an array as if it's a scalar by mistake. So this is one where I was trying to check the truth value of an array. So it's saying there's no implementation of isTrue for a load instruction. So the load instruction came from the fact that I was working with an array. And it's essentially saying, I don't know how to tell if a pointer is true or not. So all of the things that I've just talked about to do with typing are relevant for no Python mode, which is the fastest mode of compilation that Numba supports. The reason it's called no Python mode is because all the code that it generates there is native code. It doesn't make any calls to the Python interpreter or use the interpreter in any way. The default behavior, if something can't be typed for no Python mode or lowering fails in no Python mode, isn't to give up and throw those error messages back at you, but instead it falls back to a slower mode called object mode, where it does support all the functions and types. But it does that by making calls to the Python interpreter through the C API. So it goes a lot slower than no Python mode. If you want your code to go as fast as possible, then you need to have it run in no Python mode. You can force that to happen by adding the no Python equals true argument to the JIT decorator. Some functions you just can't compile in no Python mode because you'll have some types or functions that are unsupported that you need to be there. That doesn't necessarily mean that everything's lost. Even when you're compiling in no Python mode, Numba will look for loops that only use no Python compatible types, and then it will lift them out into a separate function and compile them in no Python mode. So this can work well for functions where you might have some kind of allocation or conversion at the beginning that can't be compiled in no Python mode, but the bulk of the work gets done inside an inner loop that is compatible with no Python mode. So in this example, the beginning loop is using, if an array of strings is passed in, is using strings which aren't supported in no Python mode. So it forces object mode. But this for loop down the bottom only uses integers and integer arrays. So it is no Python mode compatible, and it gets lifted out. It's helpful to be able to know what's happening inside Numba in terms of what the typing is, or perhaps sometimes to look at the generated code to be able to see why object mode's being used or what you might need to change to make no Python mode usable. So there's these methods that are all methods of JITted functions that you can call to try and find out this information. So if you want to find out what Numba thinks the type of everything in your code is, then you can call the inspect types method and it will give you a string back that will tell you that. If you want to see the code that Numba's generating, then you can call inspect LLVM or inspect ASM to get back those codes as well, if you want to understand their performance a bit better. Something that I find is quite a useful tool is the Numba command line tool, which you can use to generate an annotated HTML file containing your source code. And it will also annotate it with the Numba intermediate representation and the type of everything inside the function. Any types that are bad for no Python mode, it will highlight in red so you can see what you might need to change. And if there's any loop lifting going on in object mode, then it will highlight those loops in green so you can see where that's happening as well. The plan was to sort of like allow a bit of time sort of spending for going through the tutorial exercises. But I think, like I say, probably the best thing for me to do is to, if everyone's managed to get the materials, I'll just carry on and sort of finish the presentation talk and then just let people work through all of the tutorial in their own time, and I'll not hang around till the end of the session. So for the final part, I was going to, this is tutorial exercise 3. For that, I had some example codes for you to sort of have a go at optimizing with Numba to try and use the JIT decorator to try and make them go fast. So each of those example codes in the examples folder has got some timing and some testing code so that you can make changes and run it and then sort of see if you improve the performance, or it will tell you if any difference in the output has been introduced. Inside that same folder, there's some example solutions as well. Some of them are more optimized than others. So they've all been got to the point where they run in no Python mode, but some of them could be a starting point for further optimization rather than being considered fully optimized. So before that exercise, I was just going to over the next few slides, just share the kind of general approaches I use when I'm trying to optimize code with Numba. The first thing I would try and do is just try adding the JIT decorator to functions and then running the code, or attempting to run the code to see if it does run. Sometimes it won't because of some unsupported Python syntax, so you might need to make some modifications until it does run with the JIT decorator. Once it is running, the next thing I would do is use the Numba command line tool to generate an annotated version to see what's happening. It might be that some things are running in no Python mode already, or that there's some loop lifting going on as well. Once you've seen what's going on, you can try and convert it to use no Python mode by, one at a time, adding no Python equals true to your innermost functions, and then making changes that are indicated to the types that are indicated by your annotated version, until you've got that function to run in no Python mode, then move on to the next one. Sometimes you might do things that you think would be speeding it up, and in actual fact those things can make it go slower. So it's a good idea to, as you're making changes, just to keep an eye on the performance of the code to make sure you're speeding it up and not slowing it down. One of the things that a lot of people, or that you used to have to do in the past, is tell the JIT decorator what the types of everything is, the types of every argument are. But that's not really necessary now, because Numba can always figure it out as soon as you call the function anyway. But there is a lot of code examples on the internet on sites like Stack Overflow that are relevant to older versions of Numba where that was necessary. So you'll see a lot of these types added to the JIT decorator, but you don't need them, so it's not worth spending time doing that. Once you've got things running in no Python mode, there's often a few optimizations there's a couple of optimizations that I often find are applicable. So I'm going to talk about these. The first one is called loop fusion, and this is something that you can do if you have two for loops next to each other that are iterating over things with the same shape. So to potentially make that more efficient, you can merge those two loops into one loop by merging the bodies and getting rid of one of the for loops. Then, once you've done that, that often opens up the opportunity to do another optimization, which is called array contraction, where you convert things that are arrays into scalars if they don't need to be arrays. So in this example, if we assume that the array y, its only purpose was to store temporary results from the first loop, and it's not referenced after the for loop, then there's no reason for it to be an array now. It's part of the same loop, so we can turn it into a scalar. The reason you'd want to do that is it reduces the amount of memory usage in that for loop, so that can reduce the amount of cache thrashing in your CPU, which might lead to a performance improvement. The other thing to know is that when you're writing code, or when you're JITting code using Numba, it's a bit like C in that there's no bounds checking on any elements. So sometimes you can start finding that you're getting really weird behavior going on, or perhaps the Python interpreter is starting to segfault or throw up other weird error messages. If that starts to happen, it's possible you're going out of bounds. So one way that you can detect that is you can set this environment variable to disable JIT compilation altogether, and then run again. And then your code will be run through the Python interpreter rather than compiling the code, and that will throw up if you are going out of bounds anywhere. If that's the case, you can fix the error while you're running in that mode with the JIT disabled. Then when you enable the JIT again, if the error's fixed, hopefully that weird behavior is going to go away. I'll just skip on to my close. Like I say, I'll just finish the presentation now. There was a few things I was going to say at the end, and then I'll be around. I'll stay around for the rest of this session for people working through the tutorial if any questions come up. So something that I didn't have time to, or didn't expect to have time for in the tutorial, was releasing the global interpreter lock. If you can get your functions to run in no Python mode, then you can also get them to release the global interpreter lock by adding the no-gil equals true parameter, and then you can execute them concurrently with multi-threading. But that doesn't give you any protection from race conditions, so you need to make sure that your code doesn't have any races in it yourself. On Python 3, you can use the concurrent futures thread pool executor, but also inside the Numba distribution, there's an example called nogil.py that you can have a look at that's Python 2 and 3 compatible. I was just going to very briefly mention Number Pro, which has some other higher level features on top of Number that are mainly focused on parallelism. So you can use it to write multi-threaded ufuncs that run on the CPU or that run on the GPU. And it also gives you access to some of the GPU libraries from Python. There's a few blog posts that I've seen in the past that I've enjoyed reading that are about Number, and I thought that you might also enjoy or be interested in reading them. So all these links should be on the version of the slides that hopefully you've managed to download. These are a few places for getting more information about Number or contributing to it. There's the Git repositories. The Number Pro examples repository contains a lot of examples that will work with Number, but you will probably just need to change the imports from import Number Pro to import Number. The reason that works is that there used to be some features that were in Number Pro that have now been moved into the open source Number. There's the Number users mailing list. I don't have the link for it, but it's a Google group, so you should be able to find it by Googling. There is also, we provide some commercial support for Number. So if you need some help with accelerating your own code using Number, or the specific enhancements or feature requests that you'd be interested in, then you can come and talk to us. Also continuous hiring, so if you think it might be time to move on, have a look at the Greenhouse board or come and chat with at the Continuum booth. So after this tutorial, I'm going to be around the whole weekend. So if you think of any other questions about Number or you want to discuss anything Number related, then come and find me. I'll probably be hanging around the Continuum table when I can be. So in the next couple of weeks, I was also planning on doing a bit of Number development, perhaps live coding, explaining what I'm doing as I'm going along. If you're interested in Number internals or how Number works, then you may be interested in that. I'll probably just announce when I'm going to do that on Twitter. And finally, I did have a feedback survey for which I was going to ask for feedback. Mostly questions about the amount of time I left for the tutorial and the tutorial exercises, so don't be too harsh. Anyway, I hope in the end you do manage to get some value out of this tutorial, and I hope that you enjoy the rest of the conference. So I'm going to hang around for the rest of the session and answer any questions, or if anyone wants any help with anything in particular.